the fundamentals of alternating current electricity, specifically looking at it through the lens of the HVAC/R industry. If you've ever stared at a complex wiring diagram, or maybe listened to a humming contactor and felt just a little bit overwhelmed, you are absolutely in the right place. We are going to break down the invisible forces that literally power our world, completely transforming how you understand Unit 32.
Look, our core philosophy for this unit is super simple. We're designing for understanding, not just memorizing. I mean, sure, memorizing formulas might help you pass a written test, but genuinely grasping the why and the how, that's what actually makes you an elite technician out in the field when things inevitably go wrong.
So how do we actually lock this in? The sources recommend what they call the highly effective 3-pass study method. First, you learn. You read the concepts and physically speak them out loud. Second, you connect. Work through examples and actually explain to yourself why an answer makes sense. And finally, you prove it by testing yourself without any notes. Keep this active learning cycle in the back of your mind as we go through the concepts today. Okay, here's our roadmap for today. 1. AC versus DC electricity. 2. Magnetism and electromagnetic induction. 3. Components driven by coils. 4. Phase shifts and power factor. And 5. Impedance and power distribution. We're going to build a really solid foundation of basics before we tackle any of the complex math.
Starting us off with Part 1, AC versus DC electricity.
Think of direct current, or DC, kind of like traffic on a one-way street. The electrons just keep moving in one main direction, much like the power you'd get from a standard battery. In HVAC, you're mainly going to see this utilized in electronic boards and solid-state controls. On the flip side, alternating current, or AC, is a lot like a person pushing and pulling a swing. The direction is constantly reversing, and this is that 60 Hz alternating current that powers your standard heavy-duty equipment.
Moving right along to Part 2, magnetism and electromagnetic induction.
Picture this. You simply move a magnet near a coil of wire. That changing magnetic field actually pushes the electrons inside that wire to create voltage. Notice what's missing there. There is absolutely no battery touching the coil. The physical movement through a magnetic field is literally inducing the electrical flow. It's a completely vital concept that explains how electricity can be transferred or even created without any direct electrical connections at all.
But to make those magnetic fields truly useful for us out in the field, we have to talk about something called reluctance, which is essentially just magnetic resistance. Think of reluctance like road difficulty. If magnetic flux has to travel through the air, it's like driving on a rough, bumpy dirt road. It's tough. But if you put an iron core inside a coil of wire, well, it's like upgrading to a smooth, paved highway. The iron heavily concentrates the magnetic field, making it so much more powerful and incredibly useful for creating electromagnets.
Which brings us nicely to Section 3, components driven by coils.
So let's look at how these energized coils, which again are literally just electromagnets, actually do physical work for us. When current flows through the coil of a solenoid valve, it becomes a magnet and pulls an iron plunger, which then opens or closes the flow of refrigerant or water. A relay or contactor does something very similar. It pulls an armature to mechanically open or close electrical contacts for things like compressors or fan motors. And a transformer, well, it uses an AC current in one coil to create a changing magnetic flux, which then induces a completely new voltage in a second coil, safely raising or lowering the AC voltage without those two coils ever touching electrically. Pretty cool, right?
All right, Section 4, phase shifts in power factor. This is where it gets really interesting.
Since AC current is constantly reversing direction, we visualize it as a sine wave. Think of it exactly like a roller coaster. The wave climbs all the way up to a positive peak, drops back down to zero, plunges into a negative peak, and then returns to zero. That one full, wild trip is exactly one cycle, or 360 degrees. In the US, our power grid does this full roller coaster loop 60 times every single second, which, by the way, is exactly what 60 Hz means.
Now, the really crucial part is understanding what happens when we have multiple waves, like voltage and current, interacting with each other. Imagine two people jumping rope. If they jump at the exact same time, they are perfectly in phase. But if one person jumps just a split second later than the other, there is a phase shift. In electrical terms, that means our voltage and current are no longer perfectly lined up.
Let's see how this actually plays out when we apply different loads to our circuits. In a purely resistive load,
Think of simple heaters or incandescent lamps. The voltage and current rise and fall together. They're perfectly in phase, jumping the rope at the exact same time. But in an inductive load, like the motors, relays, and transformers we just talked about, the coil creates opposition. This causes the current to arrive late. It literally lags behind the voltage wave. This is exactly why you'll hear the acronym ELI, which we are going to decode fully in just a minute.
And here's the thing. This lag creates a real-world math problem for us. When voltage and current are out of phase, simply multiplying the volts on your meter by the amps on your meter doesn't give you the actual useful power being consumed. It only gives you what we call apparent power. Power factor is the ratio that tells us how much of that apparent power is actually being converted into true power, which is measured in watts. A perfect resistive circuit has a power factor of 1, but once those motors start causing lag, that number drops, meaning the whole system is less efficient. Finally, Section 5, Impedance and Power Distribution.
In AC circuits, we aren't just dealing with simple resistance anymore. We have impedance, which we represent with the letter Z. Impedance is the total combined opposition to alternating current, measured in ohms. The basic formula is Z equals E, which is voltage, divided by I, which is current. The source material suggests a fantastic reasonableness check for this. If you have the exact same voltage, but a higher current is flowing, mathematically that has to mean your impedance, your total resistance, is lower.
Now, I want you to think about the massive grid that actually brings this power to us. Electricity is generated at a power plant, right? But why on earth do they raise the voltage to incredibly high levels before sending it across the country, instead of just generating the 120 volts we use in our wall outlets from the start?
The answer all comes down to pure efficiency. Bumping up that voltage allows massive amounts of power to travel hundreds of miles with significantly less current. And lower current means less heat is generated in the wires, which translates to far less energy lost over miles and miles of transmission lines. Then, once it gets near your neighborhood, those magnetic transformers step in to lower the voltage back down to a safe, usable level for us.
When that power finally makes it to a typical home, it arrives as a 120/240 volt service. This is your standard single-phase 60 Hz 3-wire system. It provides 2 ungrounded hot conductors that give you 240 volts for your heavy, large loads. Think the home's main air conditioning equipment or the electric range. Then, there's a grounded center tap neutral that allows you to pull 120 volts from either hot wire to safely run all the smaller appliances and control circuits around the house.
All right, let's lock all of this in with a memory ladder. It's a great little cheat sheet for everything we just covered. Remember this flow. Alternating current creates changing magnetism. That changing magnetism leads to induction, and induction is what gives us the mechanical motion and switching we need in our valves and contactors. Also, you absolutely want to burn these acronyms into your brain. ELI reminds us that in an inductive circuit, which uses the letter L, voltage, E, leads current, I. ICE reminds us that in a capacitive circuit, C, current I leads voltage, E.
We've gone all the way from the abstract theory of electrons zooming around to the physical contactors clacking shut on a residential AC unit. So I'll leave you with this to ponder. The next time you're standing in front of a struggling piece of equipment, how will visualizing these invisible, pushing and pulling magnetic fields actually change the way you troubleshoot that contactor, that transformer, or that relay? Keep that in mind, and you won't just be a parts changer, you'll truly understand the system.